Okay, so what I plan to use... What? You're right. Yeah, sure. There's a green light, so...
Yeah, green's good.
Green is good, but is it on?
It's on for recording, yeah.
For recording, perfect. Okay.
I have to mute the ceiling speakers because of a technical error.
Yeah. Okay. So that's right. We can. Yeah. And okay. Okay. So I propose that we begin with a question that Pierre was too shy to ask in front of everybody, but which is an excellent question. So I'm sorry. Yeah, you can ask excellent questions. It's no big deal. Okay. Each time you write a theorem, you should give an idea, at least an idea of the proof. Okay.
That was not my question.
That was. Let me continue. Okay. So having such a nice, say, coherence theorem for the presentation of the algebra, it implies that the algebra is causal. In the other way around, no, it's much too hard, too strong. Okay. How do you prove that? Of course, you're going to use to prove one of these four equivalent propositions. And actually, well, in the book, the proof you will see uses the fourth one. So maybe you thought that this gives me a way to prove that this, if you replace by a here and there, no, this, I do not prove that directly. I prove this by means of spectral sequence argument. Actually, this gives me a good basis for P is bar construction, and one can prove that a certain spectral sequence collapses and gives us exactly the homology of the bar construction. And it's concentrated in the diagonal whatsoever. Okay, that's the idea of the proof. So now we can go to more exciting examples. So this was I wanted to show you the pattern as usual on associative algebras first. Now let us do non-symmetric operads. So what is our favorite toy model for non-symmetric operads? The operad way. As.
So that's the food.
Okay. So our favorite non-symmetric operad, say, is the operad as encoding associative algebras. And let us follow each steps. Okay. The method is exactly the same. The proof is exactly the same. Mutatis mutandis. Step 1. Choose a totally ordered basis for E. Okay. The space of generators. So here, when it is as, well, it's one-dimensional. So I take for basis this binary tree. Right. This is easy. Okay. Wow. Step 2. Consider a certain graded lexicographic order on trees, planar trees labeled by. Sorry. Okay, I should consider a good lexicographic order. Here, let me put that aside. I will explain that for symmetric operads. So here, let me just take a good order on, say, planar binary trees. Here, I specify that. I will explain you the full case later on. So here, on planar binary trees. Okay, I will not give you the full definition, but you know what I need to order is the space of trees with so far 2 vertices. So let me decide that this guy is greater than that guy. Okay, yeah, you have 2 elements. Which one? This is not a big deal. Okay, then choose the basis R for the space of relations. So here, and again, such that we have the leading term here and no leading term on the left-hand side. And then what I want is I would like to put the coefficient 1 here. So I will consider this, so left comb minus right comb.
So in step 2, was it equally good if you had chosen it the other way around?
Yes.
Okay.
Yeah. I will have another orientation for my diamond later, but it's not a big deal. Okay, now we interpret these relations, this basis for the space of relation as rewriting rules. So what is the rewriting rule here? We have just one, which is the left comb should be changed and give the right comb. Okay? Now we have to consider the critical monomials. So what are the critical monomials? Okay, you remember? Step 1 amounts to the generators. Step 2, the relations. So the weight 2, 1 and 2 parts of the free operad. Now in step 3, we have to consider the critical monomials. So this possibly lives in the part of weight 3 of the free operad. What does it mean? It means trees, vertices labeled by E with 3 vertices. Okay? So here, you see, so here we have just one. So here we can consider all the trees, so planar binary trees with 3 vertices, that is 4 inputs. And here there's just one which presents a subtree which is a leading term, another subtree which is a leading term. So this is a critical monomial. Inside that tree, I can see this leading term twice, and they are overlapping in a non-trivial way. So this is the unique critical tree monomial. Okay. Then step 4, you compute the graph associated to every critical monomial. So let me do the computation in this case. So in this case, we start from this critical monomial that we can first rewrite here. Okay. Oh, but we see another leading term here that we rewrite. Oh, but there is again a leading term there that we rewrite. Okay? And this term cannot be written much further. We have no leading terms, that is left combs, inside that tree. What about the other way around? If I choose to rewrite that subtree, I will get this tree. Oh, but I still have a leading term here that rewrites there. Okay? So for those of you who come from algebraic topology, what they have here that appear just under our eyes is exactly the Stashev pentagon. Exactly. The next to Stashev in the late 60s at the University of Chicago, there was MacLean, and I will make a comment about that just after. Theory. If all the critical monomials are confluent, so it's this property, that all ambiguities, when you rewrite them, the ends at the same element, then the non-symmetric operad. Well, let me make this theorem general. Okay, here I showed you the theorem on the example of us, but it actually works for any non-symmetric operad. So again, this is not the full version of the theorem. The full version of the theorem is if there exists a good ordered basis and a good order on trees, blah blah blah, which I will make precise for symmetric operas. No. Okay, so if you can find such a good basis for your operad, such that all the critical monomials they are confluent, then your operad is causal. Okay, so we gave here yet another proof that the operad as is causal, and not equivalent to the one I gave before, because before I computed the homology of the causal complex. Okay, and in this case, well, we have a nice Poincaré-Birkowitz basis for the operad itself. Alors, words without leading terms. No, it's not words, it's trees. So you consider trees where you see no leading term. Then you get a basis for the operad P. In other words, the operad P, the underlying S module, be careful, and that's not an isomorphism of the operad. You destroy the product here. This is some kind of graded version of that one. Yeah. So now you consider any trees labeled by E, and you mode out by the ideal generated by your leading terms, which are monomials. These are just one tree. It's not sum of. For instance, here we killed that tree. Okay, so this is a monomial operad. Okay, and so for instance, so this is the PBW basis. Poincaré Birkowitz basis. Okay. So you see what kind of basis do we have here? We take all the planar binary trees and we kill all the trees which have at least one left comp. So the basis here is very easy. Here the basis is made up of right comps. So this gives another proof that AS is one-dimensional in every arity. Okay, great. So this proof is completely equivalent to the proof that the MacLane coherence theorem for monoidal categories. You see, you just need to have the pentagon to have that all the other diagrams are commute.
The monomial in the end of the path is considered critical also?
No. They do not play the same role. No. It's a good question. This guy is critical. That is, you can write it in too many ways. You see? No, this is the guy. These are the guys that you do not want at all. You want to kill them, and you have two ways of killing them, say. But these guys, they play the opposite role, say, for your operad. This will give you a basis. You see? You take trees where you have only guys like this which appear. So no, they play a different role. Okay, are you ready for the full case? Okay. It's too bad that Vladimir is not here because what I'm going to explain now comes from his paper. You want to do the same to run the same method for operads. So again, behind that there is the notion of quadratic Grobner basis for an operad. I can make sense of that if you want, and you apply the diamond lemma, Bergman diamond lemma, and you get that. It relies on these. Here I cut short just to give you a method, but all this material lies behind this theory. Okay, you have an operad. So let us take Lie. So we have an operad. We start from a quadratic presentation. Okay, so we have this, and for Lie, we have the Jacobi relation of Lie. Okay. But we are back to the same problem as Ike and Volodia had during the first week. That is, now we have trees in space. Okay, we have trees in space modulo this relation. It gets really complicated, you know. You have a binary tree in space, and when I see this pattern, I can replace it by the difference of these two. Wow, what's that coset? That's complicated. So the first point here is to use, say, a planar representation of trees. So the idea is we get rid of the symmetry. Why? We are going to do homological computations. D, boundary, no. We don't need the symmetry group. We just want to prove that some complex is acyclic or some map is a quasi-iso. It has nothing to do, say, with the symmetry here. Okay, so first, the idea is to introduce the notion of shuffle trees. So the idea goes back to the paper of Erikov-Beck, and then Lutsenko and Koroshkin wrote all these di-element lemma for the opera. So what is a shuffle tree? You take a tree in space, say, something like that, seeds in space, and so the tree has some labelings on the leaves. Up, 6, 5. Okay. You see, so maybe you have this tree which lives in space. Okay, so far it's in space. You cut the ball, you see it flying in the sky. But then I want to project it on the space. So what do we do? Well, we take this labeling of the leaves, and so we take, so 1 is the smallest one. So we label the output by 1, and we do always this. So 4, 5, here it's 2. Then when I look at this tree, I have 2 and 4 incoming, so I choose 2, 1, 2, and I choose 1. Okay, it's just I rewrote things. And now when you push that on the plane, you have to make a choice of the order of the corollars. So what do? You always choose to put 1 left, you put 3 on the right one, and so you take that order, the order which is given by these numbers, okay? So I first put 1, 3, 6, I put 5, 4, 5 like this, then here I have 2 and 4, so in that way, 1 and 2 in that way. And this gives me a planar representation of my tree, okay?
How do you choose those numbers? 1, 2, 4?
I consider this vertex. And here I have 3 leaves incoming, and they're labeled by 1, 3, 6. I choose the smallest one. You see, what is a shuffle tree? It's a planar tree such that at each vertex, when you read the leaves from left to right, the numbers increase. Why not? So now I can work with these guys. So you should tell me, okay, so far this is not a good way to write the operad Lie if I want to use this basis for trees in space. You're completely right. I have to write again Lie in that way. Let me try. So is that a shuffle tree? Sure. You see, 1, 2, 1, 3. That's okay. So that's a shuffle tree. Now this is not a shuffle tree. You see, because here I have 2 and this is 1, and 2 has no right to be on the left. So, but this is the signature representation of the symmetry group. Okay, so I can choose to put that in the other way around. So instead of this one, I will write minus 1, 2, and 3. Okay, and that is okay. This is a shuffle tree. Okay, and here again, 1 is on the right, so I should put it on the left. So I want to invert these two. But if I invert these two, it's not the bracket, but minus the bracket. So here is the Jacobi relation written with shuffle trees. Okay. Okay. Now we choose a totally ordered basis for E. Oh, again, so it's again here. This is one-dimensional. So that's okay. Wow. Okay. Now we have to go to consider a good order, say lexicographic order. I think let's say tree-wise lexicographic order on shuffle trees. Okay, so how do you decide? Give me a second. I want to keep that, yes. I want to keep that board. Okay, so you need an order on shuffle trees such that each time you graft one tree above another, that is the composition in the free operad, this is increasing. You see, so you want an order such that if I do something like that and I graft with another tree here, this is an increasing. So if this is less than another one, this is less than another one, the composite is less than the composite. Do you see what I mean? Well, anyway, let me give you an example. So what you do is the following. Okay. So let's consider this is a shuffle tree, right? It is labeled by A and B, okay? And let's say that A is less than B. So yes.
It's not quite what you had before. Before you wanted the order to be homogeneous. Okay, or you didn't mind if it was homogeneous. Okay, so the comparison doesn't even make sense.
It It does? I don't understand.
The comparison between before grafting and after grafting doesn't even make sense because it's not the same degree.
I don't understand. If here you have a tree with 2 vertices and it is less than another tree with 2 vertices, the number of vertices is preserved. 2 vertices, 2 vertices. Then here 3 vertices, 3 vertices, and the result are 5 and 5. So yes.
Okay. So sorry.
No problem.
Okay.
Nice. Okay. So what can you do from that tree? How can you recover that tree? So to that tree, you associate the following thing. You start from 1 and you read the tree from top to bottom. And then you get a word, which is AB. You read the tree from top to bottom, starting from 2. You get B. And you get the tree from top to bottom, starting from 3, and you get AC. Okay? Somehow this forgets the shape of the tree, but if I give you this, then there is a 1-1 correspondence between this labeled tree and this sequence of data. Right. Now, on this guy you consider, what did we say? Graded lexicographic order. That is, first we consider the length of this word. So here we have 4 words of words. So we have 4 words. So first the length, and then the lexicographic order. Okay? So maybe I should give you an example. Let me do an example here now. Let's, and I claim that this is a good order. So let's do it on the example of Lee. So on Lee, okay, yeah, let me do the example. So you see we have these 3 trees, okay? So these 3, I will have the word, if this is mu, 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 1, 2, 3, okay? This, the word will be mu, 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 1, 2, 3, and this will be mu, 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 1, 3, 2, okay? So then I claim that this tree is greater than, see, this tree is greater than that, which one now? Hold on, okay, this one. And that one. Let me show you just between these 2 guys. Okay? So the length here is the same, but when we compare with the lexicographic order, we had mu, mu, and mu, mu, which is bigger than just mu, mu, and mu, whatever we have after that. Is it okay for everybody? Cool. So we can continue. So we have a good, you see, we consider planar trees, shadow trees, we consider this order, and we go on.
You can only compare trees of the same type.
They have the same type here. You mean the underlying same type? No, sorry. Yeah, you're right. You do it. Here, since it's one-dimensional, the space, here I have just one labeling.
Just one labeling.
Yeah, but if I had, you see, if I have several labelings, here I consider the lexicographic order on that. You see? So for instance, if I consider, say, the same tree with B and B, for instance, I will get which sentence? Okay?
Yeah, but the first word has 2 letters because of the type of the tree.
So, sorry, say it again, the first?
The first word, so you have the length 4 there.
I don't understand. They have exactly the same number of letters. So you cannot say one is greater or bigger than the other one. The length is the same and the number of letters is the same. So now how you compare them? The lexicographic order, so you start from the first word, and this is strictly less than that. So globally, this guy is strictly less than that. Okay? Okay. So now that we have this order, we do exactly the same thing. So then you rewrite a Jacobi relation using that. So the Jacobi relation writes 1, 2, 3 minus minus okay, this is the leading term. That's the biggest term in the Jacobi relation. You have tails here. There are no leading terms. You interpret that as rewriting rules. So here the rewriting rule is. So here the rewriting rule is each time you see this shuffle tree, you rewrite it as. Well, I should maybe put that one first. Okay. We have to consider critical shuffle tree monomials. Okay. That is, we have to consider trees, shuffle trees with two vertices. And here there is actually just one. Oh, look, it's the same one. Stupid. Okay? Here we are considering all the shuffle trees. So binary shuffle with three vertices. Look at all of them. And then I want to consider these such a trees such that each subtree with two vertices is a leading term. And there's only one that you can create like this. It has to be a left comb with increasing sequence of leaves. It's just this one. There's no way. If I'm faithful to my representation, I should label this. Okay. So now I need to show you. I won't write it, so I'll show you with the computer on the slide. So I need the screen. Okay. Yeah. No. Let's wait a few minutes. So I'm going to show you the diamond for Lie. So you can start rewriting this, then you can start rewriting that. And for the first time, it's not a set theoretic thing. You see, we go out set theoretic things. It's not just I rewrite that guy, that I have sums.
Why do you write a 2 down there? Not a 1?
Sorry.
No, on the right.
Because it's a shuffle tree. If I'm faithful to that graphical representation, I say that each time that I have a vertex, I have 1, 2. Here down, at the root of that vertex, I write the smallest leaf.
Right,
Yeah,
next
but
one.
now it's a leaf.
It's 1.
Thank you.
Because it's a mistake to check whether you're awake or not. Okay. Can we see the slide? I don't think so.
Somebody has to knock on his door. Maybe.
No, it's okay.
Oh.
Great, thank you. Okay. One.
No.
Yes. Oh, that's an easy computation, but I would like to show you. And plug or?
Yeah.
Okay, yeah, right. And yep. Allez. No. I have no good movie to show you. Allez. Ready? Ah. Okay. Okay. Yeah. Let me. Sure.
I need to remember the spice.
Where is it? Above, next to. Preference. Yeah. You want me to see where it is? monitor?
Yeah.
Here it's above. This position, yeah, sure. Next to it, right. He doesn't want to move. Are you better now? No, this is not working well. Just well, okay. Give me a second. Let me try to do that again. Right. No, it's here. Allez, reviens. It's okay, that's okay, that's okay. Pas là. Yes. Ouais. So you see, you have this. You have the critical monomial. Rewrite it. So the sum of two terms. So here, you rewrite the top left comb. Okay. So the 4 part, the bottom 4 is okay. Then you can choose to rewrite the bottom part. Then you rewrite it. I think I compressed. I rewrote as much as I can. You can unfold that. I mean, in that row and in that row, I think you have 2 rewritings at the same time. Otherwise, you will get a octahedron. Okay. And in the end, you get this sum of 6 terms. So any way you choose to rewrite your guy, you do that at libitum, you always get the same element. Okay. So we had a nice picture for the algebra associated to the symmetry group. For the for the operad of associative algebras, we had the Stashev pentagon, and this is, if you unfold these 2 rows, you get some of Zadmologikov equation. So this is related to some equation. This is related to categorification of Lie algebras, Lie 2 algebras actually. So, but I have no time to explain that. Okay, let's close that. And so the theorem is the same. So if all the critical monomials are confluent, then the opera discosul and shuffle trees without leading terms from a Poincaré-Birkovich basis for the operad. Then this is an isomorphism of not S module but modules, I mean a collection. You see, we completely forgot about the symmetry group action here. So we get just here a basis. So this is the free shuffle operad, and we have exactly the same argument. So this gives another proof of the fact that the operad Lie is causal. Okay, and you can now you can do that. You take the operad of Gerstenhaber algebras. You have 2 generators. You consider that, and you rewrite. I think you have 3 diamonds in that case, and then you can prove that Gerstenhaber is causal by that way. Okay. Do you have any question about this? Yeah.
A comment. You said that when you looked at the quadratic coalgebra, you hated working in this intersection R.
Yeah.
But that's exactly what you're doing.
Yeah. Yeah. Yes. It's not that I hate. It's just no. I don't hate. I love. No. It's not easy when you give the formula like this. Here is it. Please compute the quadratic co-operad generated by that generator and correlation. Here the computations I'm doing is just on weight 3, you know. This is that's why I say it's a very coherent case. It's just, see, weight 3 implies everything. Wow! Except if I want to compute the full co-operad, I have to compute it in arity 3, 4, 5, 6, and so but sure. I'm trying to find here a good basis for the causal dual actually. This gives a good basis for the causal dual. Yes.
And does this, can you find what the causal dual is, or?
This gives a good basis for the causal dual. Yes. That's in the core of the proof. Actually. Yes, that's how you prove the theorem. Yes.
Bruno, you said this argument would prove quickly that the Gerstenhaber opera is a causal opera.
Yes.
But does it give you the causal dual?
It gives you a basis as a vector space of the causal dual. It will not give you the co-operad map. No. So that's why the distributive law method is.
Yeah, I see. Okay, you still have to use the distributive law
Yes.
method in order
Yes.
to get a basis for it. To identify the causality law.
Yeah, to identify, say, what is its shape, what's the size of, and etc. Yeah. Okay, so now we are ready to begin lecture 5, which will be the last one, and so this is homotopy algebras. So very short presentation of homotopy algebras. And in the end, I would like to say a few words about the deformations of to open the doors to John's course next week. Okay, so I would like to start with the motivation. So the homotopy transfer theorem. Okay. So what is the idea? So let me try to explain a bit more what I said quickly during the workshop. I said that if you have a homotopy retract, it's a weaker version of a deformation retract. So what does it mean? It means that I take a chain complex, another chain complex, related by two isomorphisms, two chain maps. Okay. The only thing I'm requiring here is that, I don't know which one. If I do P and I, this is not the identity of A. I do first P. Yeah, this is homotopic. So you see, the composite of P with I is not the identity, it's just homotopic to the identity. This is enough, and then I will consider I is a quasi-isomorphism. So far I don't need it. Anyway. So you see, if I and P, they were isomorphism, each algebraic structure I have on the left-hand side, I can transfer or transporter in French, on the right-hand side, and I will get the same kind of algebraic structure. Let me give you an example. First example, let me consider an operator delta acting on A of degree 1. Why not? This is not, the most important thing is delta squares to 0. And here I will consider delta to be of degree 1. Okay? What about if I try to transfer, this is the simplest algebraic structure I can consider, right? What about if I try to transfer it here? The way to transfer it is by natural means that I consider delta 1. Here, well, let's say delta. I transfer delta, and what can I do? I first do I to go from here to there, I apply delta, and I come back. That's I delta P. I read from right to left. Okay? If you represent that in an operatic way, this is that composite. Okay, now you want to check, okay, good. I transported my map. Does this map squares to 0? Let's compute it. What is delta square? P delta I, P delta I. Oh yeah, and then, so what? Here in the middle, you do not have the identity. You have P and I. And the composite of P with I is not the identity, it's homotopic to the identity. So in general, this is not equal to the identity, and so in general, this is not equal to 0. But you see, this is, say, homotopic to the identity, and if it is homotopic to the identity, then here we can use delta squares to 0, so that should be homotopic to 0. So can I make sense, precise sense of that sentence? Sure. But for this, I need to introduce a higher guy. And this higher guy is what? Well, I'm going to play with H. So let me put H exactly at that place in between the two deltas. So let us consider, let's say delta 2 to be I delta H delta P. Right? Operatically speaking, well, with trees, it gives me something like that. Okay. And so let us try to, so this is a map which goes from H to H, right? And we have a differential in this mapping space, so we can consider, we can compute the image under that differential of delta 2, right? So what's that differential? So first, what is the degree of that map? 0, 1, 1, 1, 0. Should be 3. Okay, so what's that? That is dH of P delta H delta I, alors minus minus plus P delta H delta I dH. I'm doing the computation for you. Okay. P is a chain map. So P commutes with D. So I can put dA here. But okay, I didn't say that, but D should be should anti-commute with dA. So then it anti-commutes with dA. So I can put dA here. So I'm left with.
So one of the D's should be a dA in the above formula.
No. Here, no, because this guy goes from H to H.
Oh,
Yeah.
of course.
And now I'm.
Sorry.
No. And then I do the same thing here. I is a chain map. So I have a dA here, which anti-commutes with it. Minus. The delta is here, great. That's the computation. And now what we have here is minus the guy that we have on the right hand side. So this is equal to IP minus the identity of it. Okay? When we put the identity of it, we can use the relation delta squared to 0. So what we get? We get P delta I. Oh, but that's exactly delta 1 squared. So we made precise that sentence. Delta squared is not equal to 0, it's equal to the image of a certain element under the boundary map. So this is 0 up to the homotopy delta 2. Okay. And we can continue that procedure. That is, what kind of relation do delta 1 and delta 2 satisfy? Do they anti-commute? No. Actually, they do not anti-commute. And higher up, so you have a new higher structure which appears here. Higher up, one can consider delta n by the same kind of formula. That is, P delta H to the n minus 1 delta I. Can consider this full collection of maps, right? So this is for n greater than 1, delta n has degree what? 2n minus 1 plus 1, so 2n minus 1. Okay, and I leave you to check, it's an easy exercise, that, what do they satisfy? They satisfy this formula. Okay. So you see, starting from a very simple algebraic structure on the left-hand side, just one delta which squares to 0. What we got very naturally on the right-hand side is a full sequence, an infinite sequence of operators which satisfy this relation. Okay. So now the goal would be to understand conceptually this result. If you remember, we found by hand and then by means of the causal duality theory, a nice resolution of the algebra which models the algebraic structure on the left-hand side. We had the algebra of dual numbers, and then we found a resolution of that. That was the Kobar construction of the causal dual of D, which was the free algebra on delta plus delta 2 plus etc. with a certain D2 where d2 of delta to the n was equal to the sum of it's not the same tensor. Okay, if you remember well. Okay, so now the question is, starting from a homotopy retract and an algebraic structure on the left-hand side, what kind of algebraic structure appears on the right-hand side? And it is given by the notion of cofibrant resolution. Here we have an algebra, so we could say that we have a nice model, we have several, but we have a nice model category structure here. We can find cofibrant replacement, and now I am saying that the cofibrant replacement, algebras over that, here modules over that, they have nice homotopy properties. These are the kind of structure we have on the right-hand side. So maybe I should do that exercise. So what is an algebra? What is a module over that algebra? That's a map from this to the endomorphism of H. So this for me is home from H to H. What is a map of DG algebras? Okay? First, forget the DG. As a map of algebra, you just send the generators to something. So you send delta times n to a certain map. Let me call it delta sub n. It goes from H to H. And a morphism of algebras is a degree 0 map. So the degree of this guy is the degree of that guy. Okay? But we computed the degree of these. Yeah? It's 2n minus 1. Because this guy has degree 2. Well, it's not this. Do I want to do all the computations? You take delta. You suspend delta. This is what I denote by delta. I'm not good here. Then this has degree 2. Okay? And then the generators here, these are the co-free coalgebra on delta. So delta, delta 2. But then on the cobar construction, we need to desuspend these. So actually, I need to desuspend all of them, etc. So here, it's actually s minus 1 of that. So each of these guys degree 2n minus 1. Okay, so this element should be a map of degree to n minus 1. That's exactly what we found. Then, what kind of relation do they satisfy? So now I have to check that they commute with the boundary map. So I have to apply to such elements delta 2. Let me drop the s minus 1. So up to signs, I know I'm right. Okay. And then you look at the image of that element under the morphism of algebra. But a morphism of algebra on two guys, you look at the image, and then you compose them. So the image of these elements is okay. But what is the image of that element under the boundary map? That's curly D of delta n. And saying that this is a morphism of DG algebras means that these are anagram commutes. That's exactly the formula we found. You see? So if you want to answer this problem, the homotopy transfer theorem, what kind of algebraic structure you have on the right-hand side, what you have to find is good cofibrant replacement of the algebra or operad, which models the algebraic structure on the left-hand side. Okay, that's why we are doing that. Why are we doing causal duality theory? For instance, to be able to solve such problems. Okay. Well, so is that a free theorem that you've never seen in your life? Sure, you're using that in every day, say in your life of mathematician. Why? Look. What's the name of this structure that you have here on the left-hand side? Well, sometimes this is called the mixed complex. That is a chain complex with a compatible operator delta. But if you forget about this grading, well, that's just a bicomplex. I mean, we have two differentials, forget the degree, okay? They anti-commute and they both square to 0. So you have seen that in your life, huh? Okay. So say on the left hand side I take a bicomplex, right? And what will I take on the right hand side? I will take its homology with respect to the differential. Okay? If I'm working say over a field or over any if this module is free, okay, then I can write, I can choose representative for that. So what do you have here? You have say a bicomplex. And you pass to the homology with respect to the first differential. So what is H here? That's the first page of your speaker sequence. Okay? And I'm saying that, you know, on the first page of your speaker sequence, you have a full tower of new operators. Sure, that's exactly your speaker sequence. Well, when I say exactly, this is wrong. But this is an incarnation of your speaker sequence. This is actually a lifting of the speaker sequence. Okay? Why? Look at the formula. Look at that formula. Let us try to draw the formula for I don't know what is delta 3. What do you do with delta 3? You start from a point and you want to compute its image under delta 3. Oh, sorry, it's not that formula. It's that one. Okay? So delta 3 is what? Is I delta H delta H delta P. So you first, you lift your homology groups, then first you do delta, that is you do the other differential. So you go up, so this is your delta. Then you do the homotopy with respect to the horizontal chain complex. So H actually goes in that way. So you make a choice of blah blah blah. Then you apply delta, then you apply H, and then you apply delta again. Oh, and this is your delta 3. You've seen that before. That's actually a lifting of the map D3 of your spectral sequence. What do you do in your spectral sequence? That's the staircase argument that you find in many books on spectral sequences. So what am I saying here? Here I make once and for all choices of representative of the homology group. And on these guys, I define a full tower of new operators. What do you usually do when you compute a spectral sequence? You have the first page, you compute delta 1, then you pass to the homology with respect to that delta 1, then you consider the delta 2, you pass to the homology, and so on and so forth. This is defined once and for all, but what you are doing, you are passing to a sub something and quotient, sub something quotient. This is the difference. So this is just a lifting of the spectral sequence, but the formula is exactly the same. So you've seen that theorem before. Okay, then let me try to, should I do that? I should do something quickly and give you another example. So now, so you see I chose the simplest non-operatic example. Now let's take another more operatic example. You can consider here an associative algebra structure. Okay. So now, in the same way, you can transfer that. So let me define that to be, you have two elements in H. You go from H here, you do the multiplication there, and you come back. Okay, I leave you to check once again that this guy is not associative. Okay, so for the very same reason. So again, can we make This is not a problem. This is an enrichment in mathematics. It does not work directly, so there is a nice theory to be found behind that. So we consider, say, if I denote that by, let's say, mu, or let's say nu for this one, let's say mu2 for that one, you can consider mu3 to be, this is not associative, and if I write all these trees with all the labelings, this is I, this is nu, P, I, P, same here. I will take the same tree, but I will replace that by an H. Okay, why not? What's the degree of such a map? 1. I have one H, and all the other maps have degree 0. And then an easy computation, the same, shows you that the boundary of mu3 gives you exactly the associator of mu2. So again, this is not 0. It holds true up to that homotopy. So mu2 is not associative, but it's associative up to the homotopy mu3. Okay, so mu2 is associative up to homotopy. Okay, and so on and so forth. Again, higher up, you consider maps mu(n). I want to extend this. What did I consider here? I considered all the planar binary trees, here with 3 leaves. So now I'm going to take the sum over all planar binary trees with n leaves, with a certain sign that I definitely do not want to make explicit. Okay, and when I have such a tree, I label it in the same way. The inputs I. Here it's mu. The internal edges by H, and the root by P. Okay, and I leave you to check that. What they satisfy is the following formula. The differential of mu(n) is actually the sum over P plus Q equals n plus 1. So here I have mu P, here I have mu Q, and it's for I between 1 and P with a certain sign. Okay, so that's what you get when you transfer from left to right an associative product. Okay, why not? That's a nice algebraic structure. Again, what's the problem? Okay. So, yes?
We have a strict associative on A, so it's just...
It's mu, it's not mu, it's mu, it's mu. Thank you. Sometimes I use nu for the transferred guy, but I'm not using nu here. Thank you, that's what you meant, but okay. So you see, I could do exactly the same argument here. We try to solve the operad of associative algebras. We found a cofibrant replacement, which was exactly the cobar construction of the causal dual operad, or equivalently, we found it by hand with a certain D2. And if you do the exercise, the same exercise that we did here, what is an algebra of that guy? You just send the generators of your operad. So an algebra over this is a binary product of degree 0, a ternary product of degree 1, etc. And what kind of formula do they satisfy? If I do exactly the same, I will find that. Okay, so you see, this solves that problem for associative algebra. And here the example is the Massey products. So this gives you a lifting of the Massey products. Let me make exactly the same comment. For those of you who know what Massey products are, so you take the singular cohomology of a topological space. So here you have the singular, you take the singular co-chain complex of a topological space. You pass to its singular cohomology. You consider here the cup product, and it induces higher guys there. But for those of you who know what Massey products are, they are not defined on the full H, and they do not live on H. They are defined by certain constraints, so they are defined on sub H times 3, and then they live on a coset of H. Why? Why the difference from here is because here I make choices once and for all. You see, elements which are not boundary, I cannot lift them. So here H is 0. So when the classical Massey products are not defined, for me they are 0. And the classical Massey products, they are defined on some coset because we make some lifting by hands, and we want this definition to be independent of that choice. Well, here I made choices once and for all. So this lives in H. So this is a lifting of the classical Massey products. And if you look at how people compute the Massey product, they use exactly that formula. You take ABC such that the product of A and B is a boundary. So you take that element. Exactly that. Okay. Okay, so this is somehow the question I would like to solve once and for all with operads and causal duality theory. How can we make sense of this homotopy transfer theorem? And one of the most interesting things for homotopy algebras is how you compare homotopy algebras. So I need a notion of infinity morphism. So let us see what we can say. Okay, so homotopy algebras with their infinity morphism. Okay. So of course here we consider P to be a causal operad once and for all. And what is for me here a P infinity algebra? This is an algebra over the causal resolution of P. So this is what is called a homotopy P algebra. Okay? So now what you would like me to do, I'm sure, is to unfold that definition and to tell you, well, what do they look like? P is describe the set of all P infinity structures on a given vector space. Let us do that, and I will give you, say, 3 different answers. So, have a look. We still have this. Okay, this was true for any C and any P. Okay, so here I choose to put for C P anti-Schrick, and for P I will take the endomorphism operad. Okay, and let me change everything. I don't need that. Do you agree? I just applied the main theorem to C equals to P anti-Schrick if you want, and to P equals to the endomorphism operad. Okay, let me say what it means. Maps of DG operads from the causal resolution of P anti-Schrick to end of A. This is the same as a map of degree -1 from P anti-Schrick to end of A, which satisfies the Moore-Cartan equation. This is equivalent to a map from P anti-Schrick to the bar construction of A. So each time that you have, say, a twisting morphism like this, it corresponds to a unique morphism of operad and to a unique morphism of co-operads. Okay? So theorem. I think that you proved it for the first. Yeah, sure. So Ezra and John proves it for the first time, but please allow me to give it a name. That's the Rosetta Stone. See, for operad. It's fair enough. It gives you a good idea what to visit this weekend in London. So, okay, the Rosetta Stone is what? So what do you have here? Here, these are maps of operad from that guy to that guy. But that's the definition of a P-infinity algebra. A P-infinity algebra is a map from that guy to that guy. So this is by definition. But now that we can rephrase that in at least two, and there will be a third one here, this gives an equivalent definition of a notion of P-infinity algebra. And what was that? So this is the set of all P-infinity structures on A. And what's that set? That's the set of Moror-Cartan elements in a de Gilly algebra. That's exactly what we want to do when we do deformation theory. In deformation theory, the philosophy which goes back to Delin, Grothendieck, Goldman-Nielsen, Schlesinger-Stachev, etc., is you have a problem of trying to understand how many structures you have on something. Complex structures on a manifold, etc. Okay, Poisson structure on a manifold, etc. So Kodeira-Spencer, Kontsevich, and so on and so forth. The idea is, well, try to cook. This problem should be modeled by a de Gilly algebra. Those Moror-Cartan elements are in one-one correspondence with the structures you want to study. Okay? Here is the answer for P-infinity algebra. So this allows you to do deformation theory. On the nose, you see the theory was so well built that on the nose you have your de Gilly algebra which controls deformations of P-infinity algebra structure. So here the de Gilly algebra is the convolution algebra. Okay? So degree minus 1 Moror-Cartan elements in that de Gilly algebra gives you P-infinity algebra structures. Okay. What can we do with that? We are going to solve in 2 minutes the homotopy transfer theorem. You see, again, if you have a difficult problem in mathematics, sometimes you work under isomorphism and it's simple there. Or if you want to have a very complicated theorem, you know one simple theorem, you work through isomorphism and say, oh, I have a very, very hard theorem there. Yes, no. And then now what I would like to give you is, I need to define a good notion of morphism for P-infinity algebras. We have one. Here, we have a notion of algebra over an operad. Okay, the operad might be a bit complicated, but so we have morphisms. What is a morphism? A strict morphism of P-infinity algebra is just a map from A to B, which strictly commutes with all the maps. This is too strict. Again, this is too strict. We want, say, a relaxed version of morphism. This is what I want to define. So, what can we do? Let me explain that. So you see, what is mu? A twisting morphism in P anti-Schrick and domain. This sits inside the maps You remember, this is the space of all the SN equivalent maps from there to there. And then I can use the adjunction here and pull that there. So this is isomorphic to the product over N of home of P anti-Schrick of N tensor over Sn A to the NA. I can put the product in inside the home by considering the sum over n. And we've seen that guy before. That's P anti-Schrick of A, the image, under the Schur functor associated to P anti-Schrick of A. So that guy is P anti-Schrick of A. So a P infinity structure is nothing but a map from P anti-Schrick of A to A. Okay? But what is P anti-Schrick of A? We saw that P of V, this is a free P algebra. Okay? So in the same way, P anti-Schrick of A is a co-free P anti-Schrick coalgebra. If you think at the example of us, for instance, okay, what is P anti-Schrick coalgebra? Well, P anti-Schrick, well, that was as Schrick, but as Schrick is as, linear dual tensor by S minus 1. Okay? So, what is a coalgebra over that? Up to suspension, it's a co-associative coalgebra. Okay? So here in that example, what is P anti-Schrick of A? It's the co-free coalgebra on S of A. And bar, because there's no unit in as. Okay? So if you consider the example of the operad as, P anti-Schrick is as or coas. P anti-Schrick of A is the free co-associative coalgebra. Except that, because of the suspension, I have to suspend the generators, and there's no co-unit here. I have nothing in arity 0 in as. Is that okay? Good. Okay, so we are looking at maps from P anti-Schrick of A to A. But P anti-Schrick of A is a co-free coalgebra. Well, this is nothing but the space of co-derivations in P anti-Schrick of A. A co-derivation is completely characterized by the projection onto the co-generator. Alors, so far what I should have written is I didn't write the Moore-Cartan equation. I just wrote what is a map from P anti-Schrick to end of A. And I said a map from P anti-Schrick to end of A is equivalent to a co-derivation in the co-free coalgebra. What about the Moore-Cartan equation? This map squares to 0. So what I have to put here is co-differentials. Co-derivations which squares to 0. So what I am saying here is that an equivalent definition of the P infinity algebra is a square 0 co-derivation on the P anti-Schrick coalgebra. Square 0 I know it's going a bit fast, so let me write it on an example to convince you. So for instance, mu is an A infinity algebra structure on A by that definition, okay? So the one I put here, so this is called an A infinity algebra. And I'm saying, for those of you who've seen an A infinity algebra before, this data is equivalent to d mu is a square 0 co-derivation on the co-free coalgebra on S of A. And I leave you, I really have no time and I'm sorry, maybe during the exercise session, prove that. Okay, it's very easy. Okay, good. Now, what is the definition of an infinity morphism? Well, if one P infinity algebra is a DG P anti-Schrick coalgebra, here we have maps. But actually here we have more maps than we had here. Strictly more. So definition, an infinity morphism is a map of differential graded P anti-Schrick coalgebras from, you take P anti-Schrick of A with the infinity structure A, and you go to P anti-Schrick of B with the definition, with the infinity structure you have on B. Why not? I can do that. So far it says nothing. I have to unfold a bit so that you understand it. Okay. But look, this is a morphism of P anti-Schrick coalgebras. And the morphism of coalgebras are completely characterized by the projection onto the cogenerators. So this is completely equivalent to one map which goes from here to there. Right? And then if you want to feel what this looks like for any, and this is what? For any n, you see, for any n, you should have such a map. So do I have one map? No. I have a collection of maps parameterized by P anti-Schrick. If P anti-Schrick is big, I have many maps. You see? And again, if you want, another way of seeing that is that for any P anti-Schrick of n, you have maps from that to home A times n to B. Wow. So for instance, if you consider the example asked, what is an A infinity morphism? So example, what is an A infinity morphism? So you can say that it is a morphism of DG coalgebras. It amounts to maps from TC of A to B. So it amounts to a collection of maps from A to the n to B. You see here, for us, this guy is one-dimensional. That is, for any n, you have just one map. So here, an infinity morphism is one map for every n. Okay, maybe phi n is not say twiddle. So you see, an infinity morphism has infinitely many components, not just one. Keep that in mind. Then such that, I think I really have no time to give you that. We can do that during the exercise session if you want. But please keep in mind that an infinity morphism is a collection of maps. So one notation is some kind of squiggle like this. Okay. Okay. So you see, we always have, for instance, here, inside P anti-Schrick, we can take P anti-Schrick of 1, and in P anti-Schrick of 1, we have the identity, always. So to the identity corresponds a very canonical map, say phi twiddle 1, from A to B. We always have a map from A to B, which is a chain map, actually. And then we have higher guys. It's like for structures, what is an A infinity algebra? It's a binary product. Here we have a binary product, except it's not associative. Okay. And so, yeah, I said that for a good reason, is that I need two definitions. Is that For algebras, classical algebras, we have the notion of quasi-isomorphism of algebras. What is an infinity quasi-isomorphism? If that first map, which is a chain map, is a quasi-isomorphism, then we call that an infinity quasi-isomorphism. So an infinity quasi-isomorphism is an infinity morphism from A to B, such that the first map, F1, is a quasi-isom. If the first bit, I think that Kancevich calls that tangent quasi-isom. Tangent because the first component is a quasi-isom. Okay? And you have the notion of infinity isomorphism when the first map is an isomorphism. Okay. Alors, when we define objects and maps, most of the time it's because we want to build a category. So here, yes, P infinity algebras with their infinity morphism, they form a category. That's easy to see. Can we compose such morphisms? In the way I define them, yes. So they are composable. So this forms a category. And, well, if I denote by P infinity algebras the objects, I need a notation for the morphism, so I put an infinity in front. So this infinity stands for the morphisms. Okay? So these are the objects, these are the morphisms. Right? Okay? Now, have a look. We have 4 categories so far. We have P algebras. We can consider P algebras, but with the infinity morphisms. What does it mean? Well, you know, among P infinity algebras, we have strict ones. Look, what is a P infinity algebra? It's a map from here to there, right? But P, this operad is a resolution of P. So this map may be factors through that map. In that case, all the higher operations, they are cancelled. So what I am saying is that P, by pulling back along that map, P algebras, the category of P algebras, they sit inside P infinity algebras. So this is not what I wrote so far. So let me denote that map by rho. And if I pull back by rho, I get the embedding. Okay. So here we have more objects, but morphisms are just one map. Okay, so this is a full and faithful functor. But there is another thing we can do. We can look at P algebras and consider infinity morphisms between them. So here we take the same objects, but we have more morphisms. Okay, so this category sits inside that one. So this is faithful but not full. Okay. Then we have the category where we have everything relaxed. That is P infinity algebras with infinity morphism. So here we have more objects but the same maps. So this is a fully faithful functor. And here, from P infinity algebra to there, we have more morphisms. So this is not full. Faithful but not full. Okay. So now you have the definitions, you have all of that. There are 2 things I want to do. Let's continue. Do you have any questions? I have the feeling I'm going fast there, but that's the
One question. When you defined P infinity algebras, you assumed that P was causal.
Yes.
I didn't see you use it so far.
But
Is it to have smaller models?
I use the causal construction. So you're right. No, sorry. You're completely right that so far, causal played no role.
Okay.
I just needed a quadratic presentation so far. No, you're completely right. I didn't use the property that this was a resolution of P so far. So under just definition. The algebraic definition. Now I'm going to use it. No.
But Bruno, it wouldn't make sense to call these P-infinity algebras.
I will use it in the end anyway, just for
Could
sure.
you use
but-
bulk of
Sorry, yes?
It wouldn't make sense to call these P-infinity algebras unless omega P anti-Schritt was a
No,
resolution.
okay, so for those of you, okay, what do we call infinity algebras in general? In general, we don't want to fix the model. In general, what people do is they say, look, we have P,
Use the bulk.
and here we put a cofibrant resolution of P. And what people call, actually what people call A infinity algebra is, well, Stachef this, but sometimes people in algebraic topology, they say, no, it's any algebra over any cofibrant resolution of us. Sure. Yeah. But you see, okay, there are, say, two ways that I do not want to oppose. There are two ways of doing homotopy theory with algebras. One is you do model categories, tell me if I'm wrong. One is you have model categories for operads, for algebras, and then you do model category arguments, lifting properties. So that's one way to prove the homotopy transfer theorem. But then, this is wonderful, this is beautiful, this is nice, and you can prove many things. There is, say, another way which is more based on computations and algebra, like this, causal-duality theory. So I'm going to give another proof of the homotopy transfer theorem, but for causal operads. Why is that useful? That's useful because then you will have concrete formulas to prove formality theorems. And that's exactly what John is going to use. So here you will have these Macy products, and if you prove that they are all zero, then you get a formality result. So these are the at least two ways of doing homotopy theory. Okay. Okay. You have all the definitions. So why are they good for? I propose that I prove the homotopy transfer theorem, and then we stop. And of course, I have not finished, so maybe I propose to continue a bit later, but you have the right to complain and to say no. In that case, I have problems. Maybe I propose that we have a break of 30 minutes, and then we do 30 more. Maybe 30 is definitely enough, because I want to say more in the direction of homotopy category of P algebras. So, and then I answer all your questions. Let me prove the homotopy transfer theorem quickly. Alors, homotopy algebra de Z infinity. Oh, one remark. Why did I define infinity ISO? You can check that exercise. You can check that the isomorphism in that category are exactly the infinity ISO. So you see, again, I gave you a definition. I don't like that. Let's ask the following question. What are the isomorphisms, okay, invertible maps, in the category of P infinity algebras with infinity morphism? What are they? Please describe that. They are these ones. If you can invert the first coefficient of your Taylor series, then all the guys get invertible. That's the proof. Okay, the homotopy transfer theorem in 2 minutes, and we make a break. Again, for that theorem, I don't need P to be causal. But let me write causal. P be quadratic operad, but let me say P be causal. So at least quadratic. Okay, so suppose you have a homotopy retract. Okay, and that you have a P algebra structure. I don't need P algebra. Okay, let me just say one word. We have a category P algebras, associative algebras, and they do not behave well with respect to homotopy. For instance, when we want to transfer. So when we want to transfer, the transferred structure is an A infinity algebra. What if I do the same thing and I put A infinity on the left-hand side, I transfer again? It is again an A infinity algebra. Okay? So what I mean is that A infinity algebra, this category, this bigger category, flattened is stable up to homotopy operations. So we've reached the good level, the good category to work with homotopy properties. So now let me state the theorem in full generality. You take, say, alors I say mu on the left, yes. So you take mu and P infinity algebra here, that's the data. And the theorem says that you can transfer that such that blah blah blah. Alors, there exists a P infinity algebra structure on H, let me call it mu, such that I extend to an infinity quasi-isomorphism. You see, so I is a chain map, it's a quasi-iso, but you see, there exists a transferred structure. Good, take 0 and the theorem is true. But what we want is to transfer and lose no algebraic homotopy data. So now I have a structure on the left-hand side, I transfer it to the right-hand side, and I can relate both. They are both equivalent. That's what this theorem means. This is the constraint of the theorem. And the proof is very easy once you know a lemma due to van der Laan, which was a student of Ike. I will cut this into two pieces. You have the structure and you have the underlying chain complex. So far let me work without P anti-Schwick. If you have such a data, then you can look for a morphism of operads from end A to end H. If I had such a map, I mean, look, that's easy, right? I have a P infinity algebra structure, I push along that map and I get a P infinity algebra structure. That's too naive. What you have actually, a map between the bar constructions. And we are safe. We are safe under this ISO. We have a first structure, we look at it here, we push along that map, so if you have an initial structure mu, it induces a map G nu, but then you push along the map psi, then you get another map okay, and you come back if you want to make it explicit. So here you have your map mu. Okay, that's how you prove it. Now, I think there's something you would like to see is you would like to recover the formulas we had before. So I give you just the formula for that, and we stop, and it's easy. So this is a morphism of DG co-operads. What is this guy? These are trees, co-free co-algebra, we don't care, on the suspension of end of A, and these are trees on the right. But this is a morphism of co-operads. So it's completely characterized by the projection onto the generators. So this map is completely characterized by its projection. So okay. So what I need to describe for you is this map here. What could that be? On the left-hand side, you have trees. Okay, you have trees labeled by operation in A. So let's say my operation is in U3, nu2, nu2, nu2. Why not? Okay? And to such a tree labeled by operation, I have to associate one, okay, with some good degree. But okay, so let me say what I'm considering, and then if you want, we check the degrees. Now I want to map from H to H, so H6 to H. First, I go from H into A. Then I apply my maps. And then I go back from H to A. Okay, but if you do that, you do not get a map of degree 0. You see, we have a tree labeled by maps from A to A, where A times something to A. And we want one map from H times 6 to H. If we do that, this is not a map of degree 0. So I'm sorry, I want a map of degree 0. Here what do we have? We have S, 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 and S. So here we have 4S. Okay, so forget the degrees of the nu. Let's say the nu of degree 0. Here the degree is 4 so far. And the degree here is 1. So we have a map of degree -3. How can we fix that? Let us use H. 1, 2, 3. That's 4. Okay, here's your map. So if you forget about the S now, then you take your tree, you label the leaves by I, you label the internal edges by H, and the root by P. Oh, there's a comment I will make after that. Okay, this is your map. So you see the beginning of the, you see, so far we don't have the sum, but we had sums over, okay? Now, let me explain you on the example of us, the formula. So let me do that gimmick here, okay? So you start from a nu, which goes from as anti-shriek to end of A, okay? So this amounts to a bunch of maps from A times n to A. Okay, this is that part here. What is the unique morphism of co-operad induced? So now this induces a map from as anti-shriek to B of end of A. So what do? You take a corolla here, and actually you split it in all possible ways. You iterate your delta ad libitum. Okay, so this is the delta iterated. So here you get the sum over planar trees with n leaves. Oh, 4, 5, 6. Okay, so you get that. Oh, sorry. And then, no. So you see, first you do delta iterated, and then you label each vertex by that nu. Okay, so delta iterated and then nu. So I claim that this is G nu. Please trust me. You see, so I had a map from as anti-shriek to end of A. I want a map from as anti-shriek to B of end of A. How do I create trees like this? Here I use the type of algebraic structure I want to describe. I do the delta iterated. I completely unfold the corolla. So I get that. And then I have to apply capital psi to get to B of end H and actually project. Okay? So let me do it at once. So now I label that trees. And that's exactly the formula that you have here. Okay, so that's the homotopy transfer structure for associative algebra. So if here you have only nu2 and no higher guys, so if you start from an associative algebra, here you have planar binary trees, exactly the formula we found here. Okay, If you start from an A infinity algebra, you have to consider any planar tree. Okay? Alors, to comment, I have to stop because we are all tired. I have not finished, so really we make a 30 minutes break at least, and then I will explain you other properties of infinity algebras, how we can rectify them, inverse quasi-iso, and I need to prove a theorem that John will use next week. And then I will do the case of an infinity algebra a bit. 30 minutes, no more. You can apply that to many guys. So if you apply it to the algebra of dual numbers, you get spectral sequence. If you apply it to the properad of Lie bialgebras, you get some nice trees here, which looks like exactly the Feynman diagrams. They are. So there is a lovely paper by Sergei Merkulov, where here he takes the causal dual of the properad of Lie bialgebras, and you get some lovely trees here, which are exactly the one produced by the BV formalism, Batalin-Vilkovsky, not Bormann-Vogt. So there is a very precise statement there. Okay, BV formalism is exactly a homotopy transfer theorem. Right. Okay, so let's make questions, and then let's make a break. Any questions? No, it was going too fast. Right. Okay, make a break and come with your question.
When
Yes,
you say
yes.
iterated, if we just keep on doing it, wouldn't we just get binary trees? Are you saying we do it once?
Sure. When I say iterated, is you surely have the corolla. You have trees with 2 vertices, with 3 vertices, etc. So you do delta 1, you do the partial delta once, then you do the partial delta again. And you take the collection of all the trees you can get. So you will, inside that, you will definitely have all the planar binary trees, but not only. Not only. Yes.
So where exactly were the causal property used?
No, nowhere here.
But if you want to transfer between an algebra and its homology, then you need the causal?
No. No. Then when you need to compare, give me a second. No. These are purely algebraic. I mean, and then I didn't tell you the formula for the extension of the I. That's easy. When you want the formula for the I, you replace P by H. Maybe you thought the causal property is in the infinity quasi-isomorphism. No, it's not. The causal property is when you want to compare. The causal property is exactly there for those of you who will not come again, which I understand very well. The causal property is here. At some point, in say an hour, the result I want to prove is the following one. The result I want to prove is that the key result. I want to understand the homotopy category of P algebras. So what's that? That's the category of P algebras where you localize the quasi-iso. For those of you who don't know what that means, this is quite crazy. Quasi-isomorphisms, they are not invertible. They are not. Okay, if you have one in one direction, no. So what do? Invert them. That is, instead of considering maps, you consider zigzag of maps. That is your new category. So you have a bigger space of maps. You have many more maps. Does it form a category? Oh yes, but you have to put your hands. So you take maps in the directions, and each time you see a quasi-iso, you put a formal map in that direction. So by brute force, you're forced to localize the quasi-iso. That's what you do with the numbers when you want to localize and get the rational numbers. Exactly the same thing. Okay. So the objects are the same, but the maps you have much more. And does it form a category block? So how can you describe that? So Ike said yesterday that one way is by, you put more data here, it's like putting a basis, you put a model category structure there, blah, blah, blah. And then Cullen says, no, but this is a honest category. Look, you just take the category of P algebras, but these are the objects. Sure. But then how can I add more morphisms? I have my infinity morphisms. Do they answer that question? Yes, basically yes, except that you have a bit too much maps here. You just have to mod out by a certain homotopy relation. So the homotopy category of P algebras this category is equivalent to the category of p-algebras with these new infinity morphisms, except you have a bit too much. This is just a quotient of the home set. It's not a localization. It's just you have the home set, say, oh, that's a bit too big, let me take a coset of that. So this is a honest category. Well, if this is not. Okay, so this is the main reason. And for this, you need P to be causal. And this, actually, what is behind that, well, here is a survey, and for those of you who do not want to come, you have everything. The main theorem that Kancevich needs is the following. The following assertions are equivalent. If you take A and B to be p-algebras, the first point is there exists a zigzag of quasi-iso between A and B. So that's an isomorphism here, right? So having a zigzag of quasi-iso, strict maps, huh? First, this is too much. You just need two of them. And this is again too much. If you want to prove that two algebras are related by this, you need to build this intermediate. For instance, the Gili algebra. Wow, that's too big. And here is where this infinity morphism plays a beautiful role. Infinity morphism, they can always be inverted. Quasi-isomorphism. Okay? And let me say how John is going to use that. Because he will. I will check.
That's an order.
This is at the root of Kancevich method. Kancevich says, look, if you have two de Gili algebras, they define a deformation functor. If you have a de Gili algebra, you consider the Moror-Cartan elements. Okay? Polyvector fields, blah. Now, if you have two de Gili algebras which are related by a zigzag of quasi-iso, then the deformation problems, they're the same. You see? So the Moror-Cartan elements here and there are the same. I'm going very fast for those of you who know. Okay, this was approved by Goldman and Nelson. So Kancevich said, look, I have two deformation problems, the Poisson deformation of the trivial Poisson structure. I want to prove that they are the same, therefore I will be able to deformation quantize the Poisson manifold. Oh, but that's very complicated. I have to build an intermediate Lie algebra and prove that. And what Kancevich did, he said, no, let me construct an L infinity quasi-iso between here and that. And his integrals of a graphs are exactly that. So that's exactly what you need to be able to follow John's. I think yes. I will give more details after the break, but I think you have what you need. There are so much more things to say. Question? I think we need a coffee.
Did you take 30 minutes break?
40?
14?
Where we resume at 4:30.
4:30.
It will not be recorded, it's informal. It's, let me, yeah. We do whatever you want. I come here in 40 minutes. You want